Good morning, everyone. I am Dr. U. Shakti, working as assistant professor in SRM IST. Today we will see QuickSort. Sorting is a process of arranging elements in either ascending or descending order. Here we have different methodology for solving the problems. The first and important solving methodology is divide and conquer. That is, if the problem is too large or too complex, the problem is divided into number of subproblems and the subproblems are solved individually. Then the results are combined to get the solution to the original problem. That is called divide and conquer strategy. Here, QuickSort works based on divide and conquer technology. Here, by recursively partitioning the given array into right and left halves and sorting each partition using pivot element by rearranging the array elements in such a manner that elements that are smaller than the pivot are on the left and the elements which are greater than the pivot on the right. Keep repeating this process for each partition to get the sorted array. Here for QuickSort, the input is unsorted array. Take the first element as the pivot element and we are finding the place for pivot element. And the pivot element is placed in one place, that is the splitting point. That location of pivot element, the splitting point divides the array into two halves, left subarray and right subarray. Again, the left subarray is sent to partition algorithm and right subarray also sent to partition algorithm. This is a recursive call. Recursively, the given input array is divided into subarrays till we have a single element in the array. That is divide steps. And how to choose the pivot element? There are 4 methods for choosing the pivot element. So in the array, the first element can be taken as a pivot element, or the last element can be taken as a pivot element, or random. Randomly, we can choose any element as a pivot element, or median of n elements can be taken as pivot element. Here in this example, I am taking the first element of the array is as pivot element. The QuickSort algorithm places the pivot element in the final position of the sorted order. After first iteration, QuickSort places the first pivot element in the correct place of the sorted order. So that is the splitting point where the pivot element is stored in the array is called splitting point. That pivot element splits the array into two parts. Before the pivot element, all values are less than the pivot element. And after the pivot element, the right sub-array elements are greater than the pivot element. That means left sub-array, all the elements are less than pivot element. Right sub-array, all the elements are greater than the pivot element. That is the divide concept of QuickSort. And partition. The pivot element divides the array into two parts. This process is called partition. Here pivot element placed in some split point. That splits or partition the array into two halves. That is partition. After partition, the pivot element is placed in the correct place in the final sorted order. So this is a basic concept of QuickSort. It is based on divide and conquer method. And we have two terms, pivot element and partition. What is pivot element? The first element taken as pivot element that is placed in the correct order of sorted order. So that divides array into two parts. That is partition. Next, we'll see one example. QuickSort. Partition algorithm returns split point S, which is the final location of pivot element. S splits the array into two parts. See the example. QuickSort is the algorithm name. We are passing the array A. A is the array name. L is left end, R is right end. L is the first location of the array and R is the right location of the last or last point in the right subarray. And here we are calling the partition algorithm. So normally we are taking first element as a pivot element. Here in this approach, in this example, 5 is a pivot element. The first element in the array is a pivot element. So here S is equal to partition. Partition algorithm returns the location of pivot element where the pivot element can be stored. That is a split point. It returns the split point, the location of pivot element. See here, after the partition algorithm, the array is divided into two halves. The 5 is placed in split point S. Before S, the left sub array, the range is 1 to n minus 1. And after sub array, after the split point, the right half of the array, that is S plus 1 to or right index. So here the split point, that is location of pivot element, divides array into two parts. The first part, all elements, take 2, 3, 1, 4. All the elements are less than the pivot element 5. The right side, all the elements in the second half of the array, that is 8, 9, 7, which are greater than the pivot element. Again, the first half array sent as input to the next recursive call, QuickSort. Again, the same function is called A, left and right hand is S minus 1. Again, this process is repeated till we have a single element in the array. And also see the right part, again it's a recursive call. Index is S plus 1 to R. So again it's recursive call. This process is repeated till we have a single element or all the elements are sorted. This is a basic concept of QuickSort. So here, partition algorithm returns a split point. That is a location of pivot element. Again, the pivot element divides the array into two parts. Again, the left part and right part, two recursive call. Again, the same function is called QuickSort. So this process is repeated till all the elements are sorted in the array. QuickSort operations. Unlike MedSort, QuickSort divides the array into two sub-arrays based on the pivot value. In MedSort, the array is divided into two equal parts. But here, in the case of QuickSort, two arrays can be equal or need not be equal. The size of the two array can be equal or unequal because that is based on the pivot element. Pivot element can be placed in any place. That location of the pivot element, this is a split point. So pivot element splits the array into two parts. So the two parts size can be equal or unequal. But in the case of MedSort, it divides array into two equal parts. Here not like that. That depends on the pivot element. The size of the left subarray and right subarray can be equal or cannot be equal. So what is the role of partition functions? The split point S is the final location of pivot element. It splits the array into two parts. See here, we have two A of 0 to S minus 1 is the first half and A of S is the split point. That is the location of pivot element. And after that, we have S plus 1 to N minus 1 is another sub array. So we have left sub array and the split point pivot element and the right sub array. So here the values in left sub array are greater than or lesser than the pivot element, that is A of S. All values present in the right sub array which are greater than the pivot element. So this is a concept of partition algorithm. And we will see the pseudocode for QuickSort. So input is, the algorithm name is QuickSort. Input is array A, that is L represents left index or represents the last index, right index. Here, input is unsorted array, output is sorted array. And what is if L less than R? That means when it will become L equal to R, if we have single element during division operation, divide operation, the array is, in the input array is divided into two halves recursively till we have a single element. If we have single element in an array, that is L is equal to R. That is left point and the right index points only one element because we have only one element. In that case, L equal to R. So till we have single element, the recursive function, the partition function is called. So S is equal to partition, find the split point. Again, QuickSort A of L to S minus 1. This left subarray, again it's passed to the QuickSort. Again, the right subarray S plus 1 to R. Again, this process, this is a recursive call. Recursively, the function is called divides array into two parts based on the pivot element till we have a single element. So if L equal to R, if L becomes equal to R, that is we have only one element. This recursive call will be stopped. And we will see how to find the split point. How to find the split point, that's a partition algorithm. See, this is a partition algorithm. This is the algorithm given by author Anani Levitin in the textbook Introduction to Design and Analysis of Algorithms. This is a standard pseudocode for MedSat. And so this is a partition algorithm. So for partition algorithm gives the location of pivot element, that is split point. It detects split point. So how it works? So the partition algorithm take pivot element. P is pivot element as A of L, that is first element. A of L is left index. So take the first element as a pivot element. That is first element is A of L assigned to P. Then I equal to L. J is equal to R plus 1. So we have two index pointer. I is the first index in the left side. J points the last element in the array. So we have two pointers. One moves from left to right and another point moves from right to left. So I moves from left to right and J, it points the last element that moves from right to left. Now repeat I equal to I plus 1 until A of I is greater than or equal to B. So from the left we are moving the variable I. So when to stop I? If the A of I is greater than the pivot element. So stop I. So we are taking first element as a pivot element. From the second, we are comparing the element with the pivot element. So from the left, we are finding the greatest number, then pivot element, then stop I. And then from the right, J points right element, we are finding the element which is less than pivot element. Then stop J. So in that case, if I is less than J, if I is not crosses J, that is if I is less than J, swap A of I with A of J. So then this process is repeated till I crosses J. If I crosses J, come out of the loop and swap A of I with A of J, that is the last swap will be cancelled, and if I crosses J, swap pivot element with A of J. That J is the location of pivot element, that is the split point. So what we are doing, we are taking first element as a pivot element. After the pivot element, the second element is L, the last one is J, and from the left, we are searching the element which is greater than pivot element. From the right, we are searching for the element which is smaller than the pivot element. So come back. If I is less than J, swap AJ. A and AJ. If I crosses J, at some point I crosses J, J is the location of pivot element. In that case, J is a split point. So move pivot element to the split point. So swap pivot with A of J, then that is the split point. J is a split point. Again, the split point is returned to the main function, that is QuickSort, where again the recursive call first of second subarray. Again, this process is repeated for n times till all the elements are sorted or till we have a single element in the array. That is a pseudocode for QuickSort. We will take one example. So take array A. Here the first element is a pivot element. 5 is a pivot element. And 3, we have the index variable I. I points element from left to right. J is a pointer, move from right to left. So J points last element in the array. I points the second element because the first is again is a pivot element. After the pivot, I pointer starts. Now compare 3 and 5. 3 is lesser. So from the left, we are searching for the greatest element, then 5. So 3 is less than 5, increment I. Again 1 is less than 5, increment I. Again see 9, 9 which is greater than 5. In that case, stop I. Then from the right, search the element which is less than pivot. So 7 which is greater than 5. Again decrement J. 4. 4 which is less than 5. Now see here, see the notation. I points 9 and J points 4. So I is greater than 5 and 4 is lesser than 5. Now I is less than J. So I is less than J. So swap A of I with A of J. So 4 come here, 9 will go here. So after the swapping, increment I, decrement J. Now compare I. A of I is greater than pivot, condition satisfied, and A of J is less than pivot, condition satisfied. Now I is less than J, so swap A of I with A of J. So 8 and 2 are swapped, and after that increment I, decrement J. Now I crosses J. I crosses J. In that case, if I crosses J, J is the location of pivot element, that is split point. If I crosses J, J is the location of pivot element, that is split point. Now swap the pivot element with A of J. So after that, we are having 5 is placed in the split point 4. So see here, 5 is placed in the location 4. That is the split point J. Before that, all the elements are less than pivot. 2, 3, 1, 4. And see the after the pivot 5, 8, 9, 7, which are greater than the pivot element. This is a common rule. Now, it is divided into 2 subarrays. First subarray with 4 elements. Leave the split point because 5 is stored in the correct place. Leave the split point. Take element from 0 to s minus 1 before the split point. And after the split point, s plus 1 to last element, right? That is another subarray. Again 2, 3, 1, 4. Take 2 as the pivot element and I points the first element, J points the last element. So compare. From the left, we are searching for the element which is greater than 2. So 3 is greater than 2. So stop I. From the right, 4 is greater than 2. Next, decrement J, 1. 1 is lesser than 2. The basic concept is from the left, search the element which is greater than pivot. From the right, decrement J, find the element which is lesser than pivot. Stop I and J. Now 3 is greater than 2, I points 3. J is 1, which is lesser than pivot element. Now I is less than J. So swap A of I with A of J. So 1 and 3 swapped. After swapping, increment I, decrement J. In that case, I crosses J. So now J is the location of the pivot element, that is a split point. J is the split point, location of pivot element. So 2 is stored here. Before 2, we have only one element, 1. So leave that. That is in sorted order. Again, right subarray, we have 2 elements. So we have to repeat this process till we have a single element. Because we have single element, no need to sort. If we have more than 1, 2 elements or more than 2, 2 or more than 2, we have to sort it. So 3 and 4, again P is the pivot element. After P, I and J points the same value 4. Now from left, I searching for the element which is greater than pivot. So 4 is greater than pivot, stop I. J from the right is searching for the element which is lesser than pivot. Now we have only one element, 4, which is greater. I can decrement J, 3, 3. Now I crosses J. In that case, J is the location of pivot element. That is already pivot elements in the jth place only. So that means that is already in sorted order, 3 and 4. And take the second subarray, 8, 9, 7. Take the first element, 8 as a pivot element. From the left, we are searching for the element which is greater than pivot. So 9 is greater than 8, stop I. From the right, we are searching the smallest element, then pivot. So 7 is less than 8, stop J. Now I is less than J. So swap A of I with A of J. So 9 and 7 is swapped. After swapping, increment I, decrement J. Now I crosses J. In that case, J is the location of pivot element. That is a 6. 6 is the location of the element 8. So now swap pivot with A of J. 7 and 8 is swapped. So see here, 8 is the split point. So before 8, we have only one element, no need to sort. After 8, we have only one element, 9, no need to sort. So all the operations are performed in a single array. This is in place sorting algorithm. All the operations are placed in the same input array A itself. It doesn't require any additional arrays for sorting and processing. So this is in place sorting. All the operations are performed in the same array A itself. So we are getting, finally, all the elements are in the correct place. So 1, 2, 3, 4, 5, 7, 8, 9. This is the final sorted order of input array A. So tree of recursive call. How the array is splitted. So L is left index, R is right index. Initially, we have 8 elements. The split point is 4. So before split point, one sub array 0 to 3. After split point, 5 to 7 is another sub array. So in the next level, the problem is divided into 2 parts based on the location of split point. Again, L equal to 0, R equal to 3. Again, it is divided into 2 parts. L equal to 0, R equal to 0. That is, we have only one element. If L is equal to R, we have only one element. No need to go for further division. And L equal to 2 and 3. So split point is 2. After that, L equal to 2, R equal to 1. After that, here L equal to 3, R equal to 3. So this process is repeated till we have a single element. So every time for every recursive call, we are finding the first element, pivot element location. That is a split point J. So your partition algorithm returns J. That is the location of pivot element. This is a recursive call. Every iterations, the input is reduced by some constants. So that is based on the pivot element. So C program. So QuickSort input array low and int is high. If low less than high, that is if L is less than R. That is if we have more than one elements. If low equal to high means both points same elements, so that means we have only one array. If low less than high means at least 2 elements. At least 2 elements we can go for this process. So partition function will be called. We are finding the middle element. This is split point. Partition algorithm returns split point that is stored in partition index. So based on the partition index, the array is divided into 2 parts. Array low before the partition. This is before the split point. Yes. S minus 1. One is that is first half sub array. And after the split point, partition index plus 1 comma high. That is second recursive call. So again, this process left subarray, right subarray, again is called recursively till we have a single element. This is called partition main function. So initially partition function will be called that returns the location of pivot element. That is a split point. Based on the split point, array is divided into 2 parts. That is left subarray and right subarray. Again, left subarray, recursive call. Again, right subarray, recursive call. This process is repeated until we have a single element in the array. And this is a main program. So we are getting the size of the input n and get the values one by one in elements and store it in the array A or R. That is a function for input array. And after getting the input, the QuickSort function is called. So previously we have written the QuickSort function. This function is called. After this function, all the elements are stored in an array. So print the sorted array. Now see here the partition. This is very, very important module or pseudocode. That is partition algorithm or program returns the split point. That is returns the location of pivot element. So based on this location only, return J. Location only, the algorithm divides the array into 2 parts. And so we are having pivot is A or R flow. The first element is taken as pivot element. So left index L equal to low, right index J equal to high. While I less than J. What is Y less than J? That means we have at least 2 elements. at least 2 elements. So compare. Okay, pivot element with the array element from the left. From the left, we are searching for the element which is greater than pivot. And from the right, we are searching for the element which is lesser than pivot. So after finding this pivot I and j, if I is less than j means swap a of I with a of j. Else go and swap with, if I crosses j is the location of pivot element, swap pivot element with a of j. That is the concept. That means this partition routine returns the location of the split point where this pivot element can be stored. That is split point. It returns only split point. So this is the output of QuickSort. The size of the array 6. That is, we are going to sort only 6 elements. So it will ask for enter 6 elements. So we are going to enter the 6 elements. Original array means what is the input, and sorted array is the output. All elements are in sorted order. And analysis. Again, this is recursive call tree is developed. So here there are log n levels. Each level we are going to find the maximum number of comparisons. So sum up all the comparisons at all the levels. So that gives the time complexity. So the same thing already we discussed in MedSat. The height of the tree is log n. Each level algorithm performs maximum n minus 1 comparisons. So time complexity is n log n. That is level of the tree into number of comparisons at all levels. That is t of n is equal to n log n. The algorithm basic operation is comparison. Time complexity of QuickSort algorithm is based on how many times the comparison is performed. So that is from the recursive tree, you are going to find time complexity on input size n. That is number of levels in the recursive tree into number of comparisons at each level. So if we sum up all the comparisons at our different levels, that will give the time complexity t of n. And the analysis of QuickSort best case. When the best case occurs, if the array is divided into two equal parts. So normally in the MedSort, we are dividing array into two equal parts. In the case of QuickSort, that division is based on the value of the pivot element. So the pivot element or split point, it divides the array, input array into two equal or unequal arrays. Because we cannot define the size. That should be equal, that should be equal, n by 2, n by 2. Not like that. In the case of QuickSort, that is the based on the location of pivot element. So the best case occurs when the pivot array divides the array into two equal parts. And the height of the tree is log n. So each level maximum n comparisons. The best case complexity of QuickSort is order of n log n. See here, every iteration the input is divided by 2 by half n by 2, n by 4, n by 2. So this process is repeated until we have a single element. So this is the best case. Best case for QuickSort is if pivot element splits the array into two equal parts. That is the best case for QuickSort. See the example. First, it divides into two parts, 3 elements, Next, one element, one element, one element. So the partition algorithm splits the array into two equal parts. That is two equal size. That is the analysis of QuickSort. And what is the worst case? If the input is already in sorted order, if the input array is already in sorted order, pivot element divides the array into highly unbalanced. So we are finding the subarray 1 and 2. So the size of the subarray need not be equal to size of the right array, because pivot element that is split the array into two unequal or equal parts. So here the array is not divided into two equal parts like MedSat. So size of the left partition is always 0. So if the input is already in sorted order, so we are taking the first element. So we are placing the correct same place. Before the split point, there's no more element. So entire remaining element are stored in right subarray. So this process is repeated until we have a single element. So this after partition, the left subarray is empty. During search, recursive call algorithm performs n minus 1 comparisons. The worst case complexity of the QuickSort is order of n square. So because n into n, there is n number of iterations, each iteration n minus 1 comparisons. So n into n minus 1, n squared, the time complexity of QuickSort. This is the worst case complexity of QuickSort is order of n square. Analysis of QuickSort, this is a worst case example. See here, the input is already in sorted order. We are taking 5. We are finding the place for 10. So the first element already sorted order, that will be in the same place. So it divides the array into 2 parts. So before the split point, the empty array. After the split point, it contains entire all the elements. So this is the worst case complexity. If any one of the subarray is empty or the size of the subarray is 0, that will be the case for QuickSort. Time complexity is sum of comparisons at each level. So initially n equal to 6, the top level 6 comparisons. Next 5 n minus 1 input. So 5 comparisons, n minus 2 4, n minus 3 3, n minus 4 2. So that how to find out the time complexity. So sum up all the comparisons at different levels. So 2 plus 3 plus 4 up to n. So the answer is n into n plus 1 by 2. So that is order of growth is n square. And space complexity, it does not require additional array. But in the case of MathSort, we have 3 arrays: B, C sorted array, input sorted array, output is A sorted array. So we need 2 additional arrays for MathSort. But in the case of QuickSort, all the operations are performed in the single array, input array A itself. And the space complexity of MathSort is order of 1. Order of 1 is the space complexity for QuickSort. Time and space complexity of QuickSort. Time complexity is best case n log n, average case n log n, worst case n square. So time complexity is order of n log n, best case, the average case is also order of n log n, worst case order of n square. So the space complexity is order of 1. Thank you.